Okay, so quick video today. I just have something that I have to gripe about for a bit. So if you've done any shopping for audio recorders lately, like I have, you'll probably have seen that the shiny new feature all of them are advertising these days is 32-bit float recording. And well, this annoys me. Not because it's a bad feature to have or that it doesn't make sense from an engineering standpoint, but because it gives consumers a misleading impression of what's actually going on inside the recorder. Now, to be clear, the difference between what marketing teams claim 32-bit float recorders can do and what they can actually do is not really that consequential in the grand scheme of things. Most people who buy these recorders will use them as if they were actually capable of what marketing teams claim, and they'll never run into any issues that contradict those claims. But it still annoys me that some companies aren't being totally upfront about what's actually going on inside these devices. So thus, I have a rant for you. So what is this misleading claim that I'm so upset about? Well, some manufacturers will claim that a 32-bit float sound recording will never clip, and therefore there's no need to set the gain on these devices. You see, ordinarily, audio recorders have a limited dynamic range, just like cameras do. If an audio signal is too quiet, it'll become lost in a sea of electronic noise. And if a signal is too loud, the recorder will be unable to make out any details in the sound, and it'll become clipped to the maximum possible volume. And since recorders have a limited dynamic range, it's necessary to set the gain of the input appropriately. If the gain is too high, then loud sounds might clip. And if it's too low, the sounds will be noticeably noisy. And this is a problem that 32-bit float recorders will sometimes claim to be able to solve. But 32-bit float recorders, like this one I have here, do in fact have limited dynamic range, just like their non-float counterparts. It's just that their dynamic range is so good that you'll rarely have any issues. So if these recorders don't actually have unlimited dynamic range, why would anyone claim that they do? Well, it's right in the name, 32-bit float. You see, when computers have to store numbers in their memory, they don't have the luxury of being able to use our normal mathematical notation. Every number a computer stores has to occupy a fixed, predictable amount of space in memory. It's like if someone handed you a tiny slip of paper and asked you to record a number onto it. You have to decide how to use that available space so you can actually store the number properly. If you're given a big number and decide to use tally marks to record it, for example, you'll probably run out of space on the paper. But if you use normal decimal notation, you can write numbers that are much larger. Computers have this same problem. They have to record numbers into a fixed amount of bits, but they can choose to use different strategies for recording those numbers, depending on the use case. The simplest strategy a computer could use is to simply use a base 2 counting system, where each bit represents a different power of 2. In this system, the computer can basically just count upwards one number at a time. But the limitations of this strategy are twofold. For one, this approach only allows a computer to record whole numbers, that is, integers. There can't be any fractions or decimal places, and thus we usually call this data type an integer or int. The other limitation is that given a finite number of bits, there's a limit to how large a number can be represented. With 8 bits, a computer can only count up to 255. With 16 bits, it can count all the way up to 65,535, and with 32 bits, it can reach all the way to 4 billion and change. This is usually plenty, so integers are most often 32 bits long. But there is another way to record numbers in a fixed amount of bits. Going back to our example of writing numbers on a limited amount of paper, you may realize that you can represent very large or very small numbers if you utilize scientific notation. Just write a number with as many decimal places as you can fit, and then state that it should be multiplied by some power of 10. So this way you could write the number 100 as 1.00 times 10 to the 2, and you can write 1000 without using any more space on the paper by writing it as 1.00 times 10 to the 3. And you can write small fractional numbers by raising 10 to negative powers. 1/8 can be written as 1.25 times 10 to the negative 1. Computers can utilize the same strategy, just with powers of 2 instead of powers of 10. The standard way of doing this is to utilize the first bit to represent whether a number is positive or negative, the next 8 bits to represent the exponent which 2 should be raised to, and the remaining 23 bits to represent the number which should be raised to that power. Essentially, it's this binary number multiplied by 2 to this binary number. We call these numbers floating point numbers, or floats, because you can imagine that the decimal place is shifting left and right depending on what exponent is chosen. The main advantage to floats is that they allow for representing numbers which contain fractional values. And on top of that, they can also store much larger and smaller numbers than a 32-bit int can. Rather than 4 billion and change, the largest number which can be represented by a float is this number, which is so big that it may as well be infinity for most purposes. And if you really need bigger numbers, there are 64-bit floats as well, which we call doubles. The disadvantage of floats compared to ints is that they have limited precision. Although the exponent can raise a number to be incredibly large or incredibly small, the number it's operating on still has a fixed length. To visualize this, you can imagine utilizing scientific notation with only 2 decimal places. If you start with 100 and have to add 1, well, that's easy. But if you start with 1000 and have to add 1, there's no way to do that without taking up more space. As the numbers get larger, these precision issues increase in magnitude as well, so there's often value in utilizing integers to represent smaller numbers with perfect precision. They both have their place, and the pros and cons of each is one of the first things that computer programmers will learn. But let's bring the discussion back to audio recorders. Digital recorders like these have to represent the amplitude of an audio signal using a digital number of fixed length. For example, a 16-bit recorder, like the one in my camera, will take an analog electrical signal and feed it into a digitizer, which expresses the voltage of the input using a 16-bit integer. It scales the number such that the smallest possible value will be all zeros, which equates to 0, and the largest possible value will be all ones, which in this case would be 65,535. But remember, there can't be any decimal places here. If the relative intensity of 2 samples both round to the same 16-bit number, it won't be possible to distinguish between them. Therefore, the more bits a recorder uses, the better. A 24-bit recorder like this one uses a different digitizer, which converts analog values to 24-bit integers. The numbers will still be scaled such that the minimum and maximum line up in the same way, but the 24-bit recorder will have more in-between values at its disposal. Therefore, it's possible that a 24-bit recorder will be able to distinguish the difference between values that a 16-bit recorder cannot. More bits means more precision, which means a better quality recording. So that brings us to so-called 32-bit float recorders. Your intuition may tell you that one of these bad boys will have a 32-bit float digitizer inside, which converts the analog input into a floating point number. The thing is though, 32-bit float digitizers don't exist! Nobody makes them. If I were to open up this recorder, I wouldn't find a 32-bit float digitizer inside. Instead, I would find 2 24-bit digitizers. Well, actually 4 in this case, since there are 2 inputs. But what gives? Well, each of the 2 digitizers have a different gain level. One of them has a low gain and is therefore good at recording very loud sounds, and the other has a high gain and is better for recording very quiet sounds. The input is fed to both digitizers simultaneously, and their outputs are merged together to create a greater dynamic range than either could achieve on its own. This is really similar to the dual gain output approach used by some cameras to achieve a greater dynamic range than would otherwise be possible. For example, the Arri Alexa line does this to achieve its excellent dynamic range. The difference is, camera manufacturers don't claim that dual gain output results in an infinite dynamic range. The dynamic range is really good, sure, but it's still very much finite. In the case of audio recorders, though, the combined output from both digitizers is converted to a 32-bit float, and that value is what's recorded. Do you see the problem? Although the floating point numbers used for recording the signal have a functionally infinite dynamic range, the digitizers that actually produce those values do not. A 32-bit float sound file could, in theory, represent absurdly loud and absurdly quiet sounds right next to each other, but a real recorder will never actually produce an output like that. I mean, I guess in theory they could scale the real number such that it utilizes the full range of a 32-bit float, but I doubt they're doing that. Either way, it's wrong to say that clipping is impossible, or that the gain level doesn't matter. Calling these 32-bit float recorders gives a false impression, because floats don't clip, but dual gain output recorders do. But manufacturers can get away with making claims like this because the dynamic ranges of their recorders are so good that nobody is likely to encounter a situation where their limitations become noticeable. So that's about it. Again, this distinction doesn't really matter for practical purposes. I mean, I did go out and buy a 32-bit float recorder myself, even knowing this, and I don't regret that decision. But I bought this because it was a dual gain output recorder, not because it was a 32-bit float one. It's definitely better than the 16-bit recorder in my camera, or the 24-bit recorder I have here. And no, this isn't sponsored. I just want people to be aware of what these things actually are and aren't. And I wish that marketing teams would stop making these misleading claims about what their devices can do. Some companies, to their credit, are honest and tell you that the dynamic range isn't infinite. But some claim that clipping is impossible, and I don't like that. Anyways, I hope you all enjoyed this video. My name is Cayman Crocker, signing off.